Now I want to compare this side by side with another architectural style. This time I'm going to have the same set of nodes, the 5 nodes, but you notice there is no entry point. So this is a peer-to-peer system. And the interesting thing about a peer-to-peer system is your application can choose any node to interact with. So let's take, for example, again, at time t1, I'm inserting the data A. And at time t1, I was working with, let me choose a slightly different color. I was interacting with this node. Hey, why don't you take this data and insert? The node says, sure thing. So it gets the data here. And asynchronously, it is putting it here. And asynchronously, it's also putting it in here. You might wonder what happens if the application communicated with this node. Will it know where to place the data? Yes. How? I'm going to talk about partitioning, token distribution in a little bit. But for now, let's just assume that the system has enough intelligence to figure out where the data belongs. And it need not be the node that you contacted. So at time t1, it's inserting the data here, asynchronously it's putting it in here. And like before, the moment it has successfully inserted here, it can respond back to the app and say, okay, job done. But remember, this application has the ability to contact any node to get the data, masterless. It doesn't have to ask this node. So what it does is it goes out there and says, hey, you get me the data. Replication is not finished yet. So this one comes back with nothing. This node responds back to the app and says, I have no idea what you're talking about. I really don't have any data by A, because replication was happening. In the world of CAP theorem, that's weak consistency, meaning the time taken for this replication to finish. So I'm going to use again the same thing, delta t. If delta t has elapsed, then the node will have the data. So after delta t worth of time, all the nodes can potentially be consistent. Eventually they will be consistent. Eventual consistency. However, is there a single point of failure? Not at all. So if this node is down, okay, no worries. The app has the other nodes to reach out to, highly available. And because your replication factor is 3 greater than 1, you really have no problem fetching the data from the other replica. So you have partition tolerance. So if you see, partition tolerance seems to be the common attribute. If your replication factor equals, rather I should say greater than 1, it can be equal to anything greater than 1. Well, actually, ideally it should be greater than 2, but we don't know that yet. And by the way, if you have a distributed system, why would you have replication factor equals 1? It makes no sense, right? So what kind of system is this? This is called masterless architecture. So master-slave architecture delivers CP systems and masterless architecture delivers AP system, highly available, partition tolerant. However, eventual consistency can come back and bite us. What does it mean? Well, you just inserted the data A at time t1 and you're trying to fetch A, you don't get it back. It sounds fairly innocuous, isn't it? Harmless. Consider a situation where you are a financial institution. Somebody just deposited a sum of money and you are basically printing out a report of the transactions in that individual's account. And if that sum of money doesn't show up in that report, you're going to have a very upset customer standing in front of you to deal with, right? So, and alternatively, you can also look at it as, well, you just placed an order in an e-commerce organization, e-commerce website. right? And in the past orders, your recent order is not showing up. So the user is going to wonder, hey, wait a minute, I just now paid a good amount of money ordering these items, and why is it not listing in the past orders? That can be very concerning, isn't it? So my point is, eventual consistency has its merits in certain cases, but it does possesses certain demerits in certain other use cases. Now the point is, let's try to address the weak attribute in both of these use cases. So in order for me to be highly available, that means to address this delta T when my secondary is becoming primary. And if I were to say that application, you will always find some place to put your data, I may have to build a cache. So if the system is switching over or is not available, you store the data temporarily in the cache. Cache also cannot be a single point of failure. It needs to be distributed. Cache needs to make sure that it's highly available. You also need to build another system to say, okay, the system is up and running. So all the data now going forward goes to the system, data store system, and the cache is now to be flushed onto the system. That means yet another component that reads and goes through the entire cache and puts the data in here. While you're doing this, your data, the older data is still not here. What happens if the application wants that data? So there are lots and lots of complexities that you'll have to build to address the delta T. Master slave architecture, in order to make it highly available, the cost that you end up paying is huge. Cost not in the case of, not in the unit of money. That cost could be complexity. Why don't we look at the masterless architecture and see what does it take for us to be strongly consistent? How do we move from eventually consistent to strongly consistent? What is the cost here? The cost is nothing but delta T. If you pay the currency of time, you do have the ability to deliver strong consistency from the system. Do note, what am I talking about? It's not thread.sleep. You're not going to say, hey, application, once you insert the data, go off to sleep. I'll wake you up after, some time, and then you will be able to fetch the data. No, that's not what I'm saying. Right? This delta T, right? There is a mechanism in Cassandra called tunable consistency or consistency level, a topic we are going to talk about later, which basically determines how patient your application is willing to be. I just now did an insert. Do I want to fetch that data immediately? Oops, sorry. Immediately or not? You can control that as a programmer. So once you have paid the currency of time, you actually can get all three attributes. If you pay the currency of time, you can get strongly consistent, highly available, and partition tolerant system. You tell me, to address the availability here was so complex. Here you just have to pay the currency of time. That's it. And that's using a setting that is out of the box. Which is easier? My dear friends, this is probably one of the reasons why an AP system or a masterless architecture is gaining popularity in the industry. Of course, I'm not saying this is a solution to all your problems, all your data problems. No, I'm just trying to highlight what is the core reason which is driving the adoption of masterless system. And Cassandra happens to be an implementation of a masterless system. It's Cassandra's popularity in the industry has got nothing to do with the way it is written. It's got nothing to do with the features that it offers. It's the ability to deliver CAP under certain circumstances that's driving the popularity. So this is exactly where Cassandra belongs. It's an AP system right? Just like Google's Bigtable. MongoDB is a CP system because it is master slave. RDBMS really does not fit into this because RDBMS is a you know is not a NoSQL, and therefore if I were to force fit an RDBMS in here, I probably will have to go with only consistency, right? Although it's not really the right fit here, right? But that's just a representation. So let's take a look at, speaking of good use cases, these are some of the use cases that you could potentially take advantage of in terms of positioning of Cassandra. You have to always start with V3, no questions about that. Time series data is something that you can consider Cassandra for. Order management systems like e-commerce, etc. When you're talking about media, etc., you can say playlists. So you can have millions of users around the world. Each of them can have their own playlist. You can get to that playlist in a matter of microsecond. You can have Cassandra serve the data for the recommendation and personalization engine. You can also have event logs, etc., to store the chronological order of changes in your system. And then you can replay those to figure out how your data changed over a period of time. You could do things like that. Moral of the story is, if you have data, you can store it in Cassandra. The only thing that you have to keep in mind is create the appropriate data model. Because if you don't, the penalty of an incorrect, inappropriate data model, or data model that is not necessarily the right fit for the use case, the penalty for that is huge as we move on forward. If you're looking at creating a system where data loss is absolutely a no-no, for instance, you're working in an IoT project, a smart meter transmits the data, you cannot go and say, oh, wait a minute, smart meter, you got to transmit that again. Why? Because my backend is not necessarily available. Hard to build those kind of systems, isn't it? Can you go out there and say, oops, something went wrong? User, can you please click on that submit button one more time? Probably this time I'll be able to catch it. You could do that for a human user, but how are you going to do that for a machine, for a device? No need for rollups and aggregations. Cassandra is not an analytical system. Cassandra is an OLTP. It's a online. I wouldn't want to use the word transaction, but at least for now, let's just stay with OLTP. It's not OLAP. It's not for analytics. Can it provide the data for analytics? Yes, it can. And the use case is not required to comply with ACID properties. As long as you keep these pointers in mind, you probably are going to do a great job in terms of doing the fit of Cassandra to the use case. Here are some of the case studies, freely available YouTube videos. You can watch them in terms of how the industry is using Cassandra. And by the way, is Cassandra the only masterless system out there? Not at all. The others are SkylaDB, Aerospike, and apparently there is something from University of Berkeley called AnaDB as well. So these are the systems that potentially can be used in the future, although SkylaDB happens to be not as popular as Apache Cassandra, but SkylaDB does have an industry footprint, Aerospike too, but I'm not so sure about the AnaDB. So these are basic operating tenets in terms of how we should look at Cassandra from feature perspective.